is we're going to talk about section 8.3, which is involving integrals of trig functions and combinations of trig functions. So we'll start out just by reminding you, we had this integral in section chapter 8, but just in case, remember the integral of secant x dx is the natural log of absolute secant x plus tangent x plus c. That is definitely not one that you want to have to derive every time, because it is not really an intuitive derivation. To find out that integral, what we would actually do is multiply creatively by 1 inside the integral, because that would be the same thing as the integral of secant squared x plus secant x tangent x over secant x plus tangent x. And so we could do a u substitution. And we would get that this whole big long numerator times dx is nothing more than du. So this would be the integral of du over u, which is the natural log of the absolute value of u, or the natural log of the absolute value of secant x plus tangent x plus c. And as I mentioned, that's not entirely intuitive as far as the way you come up with that. So that's one of those integral rules that I would definitely consider worth memorizing, because it's just too time consuming to have to derive that every single time. And the integral of cosecant x, when it was derived in a very similar fashion. The integral of cosecant x ends up being negative the natural log of cosecant x plus cotangent x plus c. And sometimes in some books you'll see the natural log taken into the inside and simplified in there, and get a natural log of cosecant minus cotangent inside the absolute value signs. I'm going with this form because that's the one our book uses. Okay, so these two guys, memorize them, because you will be using them quite a bit in the next few sections. Now, what if I asked you, let's start off with a softball here. What if I asked you to integrate this? Any guesses? How many trig functions do we know how to integrate? Well, we know how to integrate the 6 basic trig functions plus those functions that are derivatives of our 6 basic trig functions. So our basic trig integrals that we know from either u substitution or just the fact that they're derivatives of others, in addition to these two that we just talked about, so we have this one and we have this one, we know that the integral of sine x dx is negative cosine x. We know the integral of cosine x dx is sine x, because the derivative of sine is cosine. We know the integral of secant squared x is tangent. Integral of secant x tangent x is secant. The integral of cosecant squared x is negative cotangent x. Cosecant, cotangent, negative cosecant. And the other two that we did with u substitution in section 5.5 were tangent x, which is negative the natural log of absolute cosine x, and cotangent x, which is the natural log of absolute sine x. So these are our basic trig integrals that we had on that list, including those two, a list of things that we should know how to integrate. This doesn't fit anywhere on there. If it's not one of my basics or a sum or difference of some of my basics, the next thing I ask myself is, can I use u substitution? Could we use a u substitution on this one? Good grief. Yes or no? U substitution or no? Are you sure? Is one of those functions the derivative of the other one? But thank you for picking an answer, though, and saying something. If I just let u equal sine x, du would be cosine x dx, and this would just be the integral of u cubed du. And the integral of u cubed du is 1/4 u to the 4th plus c, or 1/4 of sine x to the 4th plus c. So a lot of times when you have products of trig functions, if one part is the derivative of another part, you can do just a straight u substitution. What if you had something like the integral of tangent to the 5th times secant squared? Well, what's the derivative of tangent x? It's just secant squared x, right? So if I let u be tangent x here, then du would be secant squared x dx, and this would just be the integral of u to the 5th du, which is 1/6 u to the 6th, or 1/6 of tangent x to the 6th, and then plus c. So I don't want you to start these by thinking, oh, I've got to do a whole lot of simplification. You always want to start by asking yourself if you can do a basic integral. Can you do it with just plain old u substitution? Okay. If you can't, then we may have to bring in some trig identities to be able to rewrite it. Now, we've done some trig identity rewrites in the past, but just a reminder, a couple of the trig identities that you're going to need to remember are your Pythagorean identities, which are sine squared x plus cosine squared x equals 1, tangent squared x plus 1 equals secant squared x, and cotangent squared x plus 1 equals cosecant squared x. So those are your Pythagorean identities. And we also had half angle identities and double angle identities. The double angle we don't use quite as much, but you will need to know that, for example, sine of 2x is 2 sine x cosine x. And then there's a couple different ways that we can write the cosine of 2x. And remember, these are on the back of the front page of your textbook. Just a reminder. So for those of you that have a hard copy, we talked about this the other day. We've got the half angle, double angle, Pythagorean, and reciprocal identities. But the cosine of 2x can be written as cosine squared x minus sine squared x. I'm pretty sure they're in there somewhere. But yeah, just remind me, okay? Okay, you bet. And then the biggest ones for this particular section that we haven't used as much are the half angle identities. We've used them a little bit, but we also need to know that the sine of 2x is 1/2 of 1 minus cosine 2x, and the cosine of 2x is 1/2 of 1 plus twice the angle. So actually now you have all the ones that we're going to primarily use. All right. So if we can't just do a trig integral using a basic substitution as we did on the first couple, we may have to rewrite these. Okay. So let's say we had, instead of sine to the third times cosine to the first, what if we had sine cubed x times cosine cubed x? Well, what makes this harder? If that was just a single cosine x, then we have a u cubed du. The problem is, since that's cubed now, I have an extra 2 copies of cosine x that would not be involved in my du. When that is the case, what we're going to do is say, okay, I could pull one of those cosines off and sit it there with the expectation that it will be involved in du. So all I did here was I rewrote cosine cubed as cosine squared times cosine. If I pull off this cosine x, and I'm hoping that that is going to be my du, what must u be? Well, u would have to be sine x, because the derivative of sine is cosine. So if we pulled off one of these cosines, could we use any of these formulas up here to rewrite cosine squared in terms of sines? Of course we could. So cosine squared x, remember we have sine squared x plus cosine squared x equals 1. So that would mean that cosine squared x is 1 minus sine squared x. So we have sine cubed x times 1 minus sine squared x times cosine x dx. And I personally would go ahead and do my u substitution here before I multiply it out, just because it'll make the writing a little bit shorter. My u will be sine x, my du will be cosine x dx, and this will be the integral of u cubed times 1 minus u squared du. How do we integrate that? We multiply it out and integrate term by term. So that will be the integral of u cubed minus u to the 5th du, which is 1/4 u to the 4th minus 1/6 u to the 6th, where we have 1/4 sine x to the 4th minus 1/6 times sine x to the 6th. Oh, plus c. I was going to say plus c and wrote dx instead. Okay. So if we have either sine or cosine raised to a positive odd power, you can pull one of those off and use the Pythagorean identity to rewrite the others in terms of the opposite trig function. So what if we had something like sine to the fifth of x dx. Well, what we'd really like is if we had a cosine x over there and just make it a u to the fifth du, but we don't have that. But we do have a sine function raised to a positive odd power. So I'm just going to pull off one of those sine functions. Now remember, whatever I pull off over here to the side, I'm hoping that is going to be du, at least up to a multiple of it. So if that's going to be du, u would have to be what? Whose derivative is a sine? It's going to have to be a cosine, right? So I'm going to leave it as just cosine, and we'll take care of the negative sign here in just a minute. So if I'm going to try this, my u would be a cosine and my du would be negative sine x dx. That's where I want to go if I pull that off to be du. But before I can do that, I've got to rewrite these remaining sine functions in terms of cosine. So I'm going to rewrite sine to the fourth is sine squared times sine squared. And I'm going to use the Pythagorean identity on both of these. Sine squared x is 1 minus cosine squared x. So I'll have 1 minus cosine squared x times 1 minus cosine squared x times sine x dx. There's just no getting away from the trig identities. There really isn't. All right. Now, I'm going to go ahead and do this u substitution. So this will be, I need a negative sign in there to make it a negative sine x, and I'm going to reverse it with a negative out front. So I will have negative the integral of 1 minus u squared times 1 minus u squared du. Or that's negative the integral of 1 minus u squared is minus 2u squared plus u to the fourth du. So we end up with negative of u minus 2/3 u cubed plus 1/5 u to the fifth, or that would be negative cosine x minus a negative would be plus 2/3 cosine cubed x minus 1/5 cosine to the fifth x plus c. And I should have left myself a little more room. When do we do this? When we have either just a sine to a power or a cosine to a power, and at least one of them is odd. You can just pull off one and leave an even power left and use your Pythagorean identities. Yes. Yes, you would. So if you had sine to the 7th x, you'd have to pull off one of them, but then you'd have a sine squared, and a sine squared. So you'd have a 1 minus cosine squared, 1 minus cosine squared, 1 minus cosine squared. The higher the powers, the more arithmetic and algebra that go into it. Now, what happens if you don't have an odd power? We've done this one before. Back in section 5.5, they gave us an option. When you have only even powers of sine or cosine, that's when you use the half angle formula. And that would be 1/2 of 1 minus cosine of twice the angle. So if that had been a sine squared of 4x, this would be a 1 minus cosine of 8x. You double the angle. Half the exponent, double the angle. All right, so this part we know how to integrate. We have 1/2 the integral of 1 minus cosine 2x dx would be 1/2 of the integral of 1 dx is x. The integral of cosine 2x is 1/2 sine 2x, and then plus c. When do we use the half angle identity? When we don't have an odd power of sine or cosine. Now these get messier in a big hurry when we only have even powers, because when you have to use that multiple times, you're going to have to multiply it out and all that good stuff. So for example, what if we had sine squared of 2x times cosine squared of 2x? I can't pull off either a sine or a cosine out here to be du, because if I did, it would leave just, say, one sine, and I can't use the Pythagorean identity on that, at least not easily. So since they're both raised to even positive powers, what I'm going to do is I am going to use the half angle identity on both of them. Sine squared of 2x is 1/2 of 1 minus the cosine of 4x. Cosine squared of 2x is 1/2 of 1 plus the cosine of 4x dx. Half the exponent, double the angle. The problem is when I go to integrate this, I still can't. My effective power here, if I combine these, I have trig functions all together raised to like a 4th power, so to speak. But if I simplify this, I have 1/4 from the 1/2 times 1/2. Multiply this out, I have 1 minus cosine squared of 4x. So what do you think I do next? And crying is not an option. That's not an option either. Well, we've gone from having 2 powers of 2, so effectively power of 4, to down to a power of 2. We're making progress. Could we just do it again? Yeah. So I'm going to replace this with 1/4 the integral of 1 minus cosine squared of 4x is 1/2 of 1 plus the cosine of 8x dx. Now, personally, before I integrate, I like to combine any like terms. So I would simplify that just a little bit before integration. I have a 1 minus a 1/2 is a 1/2. And then I have minus 1/2 times the cosine of 8x. So I have 1/2 minus 1/2 cosine 8x dx. And if you want to, you could then factor that 1/2 out front. I'm just going to leave it this time, but that would be 1/4 times the integral of 1/2 dx is 1/2 x minus the integral of cosine 8x is 1/8 sine 8x, and then plus c. So we get 1/8 x minus 1/16. oh, sorry, 1/16 times 4 would be 1 over 64. Forgot I was multiplying through there. Sine 8x plus c. Now keep in mind, guys, that when you do this many substitutions inside an integral, if you just take the derivative of that, it's going to be hard to check that it's right. There would be a lot of rewriting using trig identities to check your answer as well. So just keep that in mind. But these are just ideas about how you can go about rewriting functions that you don't know how to integrate using your basic integration techniques. All right, let's take about a 5-minute break, and then we will come back and look at a couple more. What if, have I given y'all a chance to look this over? This is just what I've been saying. If you have sine to a power times cosine to a power, or it could be just cosine to a power or just sine to a power. If those are positive integer powers, if one of them is odd, pull off one of those trig functions and use the Pythagorean identity and use substitution to rewrite the rest. Now, if they're both odd, if it was like sine to the third and cosine to the third, you can pull off either one you want to and just rewrite the others in terms of the second trig function. You have choices in that. If they're both even, though, if you have a sine to an even power or a cosine to an even power, or sine times cosine where they're both even, you're going to rewrite them using half-angle identities. So this is just to represent that we're going to use a half, because that I don't mean for that notation to be kind of confusing, but you're going to rewrite using half-angled identities if you're only even powers. So let's, like we did here, we had to use a half-angle identity twice. Okay. Now, what if you had, let's say, how about this one? So I've moved to tangents and secants here. Why are tangents and secants linked similarly to sines and cosines? Well, the derivative of a sine is cosine, the derivative of cosine is sine. So when you have combinations of those two functions involved, a lot of times you're going to be able to do a u substitution of some sort. Same thing with tangents and secants. The derivative of tangent is secant squared, the derivative of secant is secant tangent. So if you have some combination of those two functions, a lot of times you can pull off either a secant tangent or a secant squared to be du. This would be du if u equaled just tangent. So I would let u equal tangent x, and du would be secant squared x dx. So this would just be the integral of u to the 5th du. Did I already do that exact problem? It sure feels familiar. I did. Oh my goodness. Which is u to 1/6 u to the 6th plus c. Okay. I'm going to start doing roll call, though, because I'm beginning to wonder how many of you are here. I know Miguel was here. I know that Annabeth is here because y'all said something to me. So just type here into the chat line if you're still here. All right. So what are we going to do when we don't have, where we can just pull off a secant squared? Really? We're down to 3? All right. What if we had something like let's make this a 5th. So let's say we have a tangent to the fifth times a secant cubed. Okay, so what might we try here? If we have a tangent to the fifth and a secant cubed, I can't just pull off a secant squared because I can't use the remaining secant. I can't use the Pythagorean identity to rewrite it in terms of tangent. So what's the other derivative involving secants and tangents? Well, it's secant tangent, and that's the derivative of secant. So let's try pulling off a secant tangent. So I'm going to pull off one tangent and one secant. Okay. If that is what I've pulled off sitting over here waiting to be du, what must u be? If this is going to be du, then the u that we're going for is going to be secant x. So du would be secant x tangent x dx. So I've got a secant squared here, but I'm going to have to rewrite this tangent to the fourth in terms of secants. So I'll use the Pythagorean identity. This is tangent squared times tangent squared times secant squared. And remember, this secant x tangent x that we pulled off over here to the right is hopefully going to just be du. Pythagorean identity with secants and tangents. This would be tangent squared x is secant squared x minus 1 times secant squared x minus 1 times secant squared x secant x tangent x dx. That is an S there. That looks like a 5. So I'm going to do my u substitution that I was hoping for. This would be u squared minus 1 times u squared minus 1 times u squared du. Integrate that. To be able to do that, I'll have to multiply it out. This would be u to the fourth minus 2u squared plus 1 times u squared du. So that will be the integral of u to the sixth minus 2u to the fourth plus u squared du. Integrate term by term. We'll have 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u cubed plus c. Well, that'll be 1/7 times secant to the 7th minus 2/5 times secant to the 5th plus 1/3 times secant cubed plus c. Notice the bigger the exponents get up here, the bigger the painful process is as far as how much you have to go through as far as simplification is concerned and all that good stuff. But if you have a product of secants and tangents, so we have the integral of tangent this is the one you want? Okay. Alrighty. Alright, so when we have a product of secants and tangents, if secant is raised to an even power, I guess that's why I have an N. We can pull off a secant squared x to be du and rewrite the remaining secants in terms of tangent using the Pythagorean identity. Secant squared x equals tangent squared x plus 1, which means that tangent squared is also equal to secant squared x minus 1. So once you do that, you'll use u equals tangent x, du equals secant squared x. Okay? If m is odd, you can try to pull off a secant tangent and rewrite the remaining tangents in terms of secant, still using the Pythagorean identity, but it's tangent squared x is equal to secant squared x minus 1. And then you would have u is secant x, du is secant x, tangent x. Now if n is even and m is odd, so if both of those things are true, you just get to pick. You can either pull off a secant squared or you could pull off a secant tangent. It just depends on what you would rather do. If neither of these is true, we don't have a method. You might try rewriting in terms of sines and cosines. Or something to that effect. Okay, so these are just guidelines. They're just suggestions and mentions of ways that you could possibly rewrite. And if they don't hold true, you just have to try something with some other trig identity. But you've got to just try something. And these guys, if this was replaced with cotangent to the m and cosecant to the n, we would do the same things, except we would use the identity cotangent squared x plus 1 equals cosecant squared x. So the guidelines here for secants and tangents have completely analogous statements for cosecants and cotangents. And that's because of the symmetry of their derivatives and the way they're related as well. So let me pull up the homework in this section while you guys are getting that written down if you so choose. All right. Avery, pick me a number between 1 and 17. Yes, please. 6. Okay, so we're going to look at number 6. For my personal problems, is it okay if can I move this, or are you still writing? All right, so on number 6, we have an integral from, or of, sorry, cosine cubed of 3x sine to the negative 2 of 3x. Excellent choice, Avery. Okay, so this one's a little bit different. We don't have positive powers, but I do have a cosine to a positive 3. It's to a positive odd power, so I'm going to pull off a cosine. Over here to the right. And that cosine that I've pulled off over to the right is hopefully going to be du up to possibly a constant multiple. If that's going to be my du, though, u must be a sine. This is a sine. This one I'm going to have to rewrite. So I'm going to rewrite that cosine squared of 3x as 1 minus sine squared of 3x. And I have that times the sine to the negative 2 of 3x. Okay, so even though one of my powers was not a positive constant or positive integer, I still was able to use the fact that I did have one of those to a positive odd power and pull that odd term off. Now, since I pulled this off over here to be du, my u will be sine 3x, and my du would be 3 cosine 3x dx. So I'm going to multiply by 3 and reverse with a 1/3 out front. And we will have 1/3 the integral of 1 minus u squared times u to the negative 2 du. Everybody okay right here? Okay. How would we integrate that? We would have to multiply through, and we'll have 1/3 the integral of u to the negative 2 minus u to the 2 times u to the negative 2 is just 1, and then du. Integrate term by term. We'll have 1/3 the integral of u to the negative 2 is negative u to the negative 1 minus u. So we have 1/3 times negative 1 over u minus u. And I'm going to put on my plus c. So we have negative 1 over 3 sine 3x minus 1 over 3 sine 3x plus c. Now they probably would not leave their answer like that in my math lab, because 1 divided by sine, remember, is the same thing as cosecant. So they would probably write that as negative 1/3 cosecant 3x minus 1/3 sine 3x plus c. Questions? All right, Brian, you want to pick a number between 1 and 17? Okay, Brian does not want to pick a number between 1 and 17, I guess. How about Alexia? $15 sounds good. Let's look at number 15. On number 15, we have 7 times tangent x times secant cubed x dx. Now remember, when we have products of secants and tangents, what we're going to do is we're either going to pull off a secant squared and rewrite everything else in terms of tangent, or we are going to pull off a secant tangent and have everything else in terms of secant. Which one do you think we should do in this case? All right, let's try that. If I pull off one secant and one tangent, I'll have a secant x and a tangent x over here. So I've pulled this tangent over here, and so I'm left with just a secant squared x. Excellent idea. If this is what we pull off over here to the side, that is sitting there waiting to be du. If that's going to be du, then u has to be a secant. And we have u squared right there. So if u is secant, du is secant x tangent x dx. And so that would be 7 times the integral of u squared du. Or we would have 7 times 1/3 u cubed plus c, or 7/3 u to the third would be secant to the third plus c. Questions? All right, Annabeth, you want to pick a number between 1 and 17? Well, of course we can. But y'all are going to have to tell me what to do. I'm going to have to come up with a way that you can have a daily grade. Do what? Oh, in the class. Okay, I'll try to make it straightforward for you guys. I'll try to lead you if we need to. Okay, so things to keep in mind when you're dealing with cosecants and cotangents. Remember, the derivative of cotangent is negative cosecant squared, and the derivative of cosecant is negative cosecant x cotangent x. So when we're trying to pull off one of these to be du, we need to either pull off a cosecant squared or a cosecant cotangent. Based on the fact that the cotangent is all in the bottom of this fraction, which one of these do you think we would still be able to do? Yeah. What we typically do when we have products of secant or cosecants and cotangents is we either try to pull off a cosecant squared to be du, or we try to pull off a cosecant cotangent to be du. Yes, we would pull off a cosecant squared, because the cotangent's here in the bottom. I don't have a cotangent up here in the top to pull off. So I am going to pull off a cosecant squared, and that would leave a cosecant squared here over cotangent squared here, and I'm pulling off one cosecant squared to sit out here and be du. If that is going to be du, then u is going to have to be a cotangent. So what we're going to have to do is this part I want to hold on to that. That's my du. Everything else over here I want to try to write in terms of cotangent. This part is good. This part I'm going to have to use the Pythagorean identity on it. We know that cotangent squared x plus 1 equals cosecant squared x. So cosecant squared x minus 1 is equal to cotangent squared x. So this would be 3 times cotangent squared x plus 1 over cotangent squared x cosecant squared x dx. So if this is my u substitution, I'm going to need to multiply by a negative sign in there to get my negative for my derivative, and I'm going to reverse it with a negative sign out front, and I will have negative 3 times the integral of u squared plus 1 over u squared du. And that would be negative 3 times the integral of u squared over u squared is 1. 1 over u squared is u to the minus 2 du. Any questions up to this point? All right, so we will have negative 3. The integral of 1 du is just u. The integral of u to the negative 2 du is negative 1 over u plus c, or it's negative u to the negative 1. So we get negative 3 cotangent x plus 3 over cotangent x, which is perfectly fine, but usually they won't leave division by a trig function because they can rewrite it in terms of its reciprocal function. Dividing by cotangent is the same thing as multiplying by tangent, so that would be plus 3 tangent x plus c. Questions? Have you guys got this written down? Can I move the page, or are you still writing? Where are you talking about? I'm sorry. Here? If I'm using u to be cotangent x, the derivative of u is the negative of cosecant squared. I have a cosecant squared, so I need a negative cosecant squared, so I just multiplied by negative 1. But if I multiply by negative 1 on the inside, I need to reverse it with a negative 1 on the outside. So I mean, you could think of those as a negative 1 and a negative 1. I just put the sign in. Okay. Now let me give you just a different kind of take on this. Guys, what you have to be willing to do to be good at integration is to be willing to do something. Even if you don't know if it's going to work, you've got to try something. And so let's say we forgot, you know, okay, I've got an even power of cosecant here, so I could pull off a cosecant squared. Let's say we're just stressed out and we've forgotten that. Is there any other way I could rewrite this function? Well, yeah, I know the basic definitions of my trig functions. Cosecant is 1 over sine. Cotangent is cosine over sine. So this would be 3 times the integral of 1 over sine to the 4th x times sine squared x over cosine squared x. I just flipped the bottom fraction to multiply. So that would be what? This one would be, yeah, 1 over sine squared cosine squared. Yeah. So this one we go, well, crud, I don't know what that does for me in this particular case. Because frankly, for this one, it doesn't do anything. But sometimes when, I should have been thinking further ahead, but sometimes if you don't have any ideas what to do, try rewriting it in terms of sines and cosines. This one kind of got us, we just kind of got stuck because we've got a 1 over sine and a 1 over cosine, so we've got like a secant cosecant, which is no good as far as trig identities are concerned. But that doesn't mean that it's not a useful kind of exercise to work on. You might say, okay, well, that didn't help. Could I rewrite this sine squared as 1 minus cosine squared and then break it up? Well, maybe. So at least give it a shot as far as if you can't do one of your, one of our basics, at least try rewriting it using your basic trig identities. And sometimes when you just don't have any other options, it'll work best if you take it back to sine or terms of sines and cosines. This one, like I said, I wasn't thinking far enough ahead, and this one didn't get us anywhere. But at least give it a shot if